Welcome back. Today we're going to be looking at inverses and radical functions as we finish up Chapter 5. Don't forget to be preparing for your test, your Chapter 5 test coming up, reviewing the videos and notes and exercises that you can, practicing practice problems so that you feel fully prepared for Chapter 5 test. We're going to start with a little bit of review. A lot of today is going to look pretty familiar. We're going to add some domain and range notes to what we've already talked about with inverse functions. So hopefully this feels a little like review. Jumping off, it's a review try at one saying, hey, can you show me that two things are inverses of each other? This is the blue function and this is the red function. Remember, the way that we show inverses is we compose or composite the functions. So we say, okay, what is f of f inverse of x? We put one function inside of the other. So on the outside, we're going to have x plus 5 over 3. And then you erase that x, and wherever x is, you plug in the red function with parentheses. 3x minus 5. And then we solve, and we'll probably see that those 5s are going to go away. And we're going to be left with 3x over 3. And then the 3s are going to go away, and we're going to be left with x, which is what we wanted. Now if we do the exact same thing in reverse, and we say, what is f inverse of f of x? We are hoping to get the exact same answer and that answer to be x. Let's find out. Out on the outside, we have a big blank. We have 3 blank minus 5. That blank standing for the variable, standing for the x, but it's not a blank. It's going to be the blue function of x plus 5 over 3. And we're going to see those 3's cancel out again. X plus 5 minus 5. X is our answer. We have shown that two things are inverses of one another. All right, let's keep going. Now we're going to find the inverse of a radical, which is a little bit new in this section. But the steps are exactly the same as finding an inverse, where you rewrite it with a y. You switch x and y as the main step. That's what inverse means. It means switching x and y. And then you solve for y. So we're going to cube both sides and end up with x cubed equals y plus 4. We're going to subtract 4, and then with y equals x cubed minus 4. Remember, we don't leave it as y because it is an inverse of x, so we're going to write f invert x equals x cubed minus 4. And if you wanted to use the steps from try it 1 to prove that that's an inverse, you could use our answer and the original function, plug them into one another, both directions, and see that these two things are inverses. All right, let's keep going. Now we're going to add the domain restriction. Now we're going to add the thing that changes up this section just a little bit. And it's just saying, hey, sometimes you have a non-invertible function. So if you remember back from graphing functions, this looks like the normal parabola shifted up 1, right? And remember, the thing that an inverse needed to pass was the horizontal line test. And in 2 spots, that doesn't pass the horizontal line test as soon as we look at it. And so what this problem is saying is, hey, we can make it invertible by restricting our domain. Our function is actually not the whole thing. Our function is just anywhere that x is equal to or greater than 0. And now it passes the horizontal line test. And now this is f of x restricted. Now that it passes the horizontal line test, we are allowed to invert it. And so we're going to invert it. Y equals x squared plus 1. Switch them. X equals y squared plus 1. Move the 1 over. Y squared equals, what would that be? X minus 1. And then square root it. Y equals big old square root of x minus 1. But wait, weren't we supposed to introduce a square root with a plus or a minus? Yes. This is why that domain restriction was so important, to eliminate this option. So now we have to look at our domain restriction and say which of those two is going away. So if we look at our domain restriction, we'll see that x has to be bigger than 0. That means our domain was 0 to infinity. But the domain and the range switch when we invert it, right? So that means our range of f invert x is going to be 0 to infinity. So our y value is positive. And if this is our y value, we only take the positive side because we know it has to be positive. And so we can write our function f invert of x is equal to the positive side of that square root. So that's kind of why that domain restriction is important before you can actually find the inverse of a non-invertible function. If we didn't have that domain restriction, then we would definitely have to say, hey, we're not allowed to invert that. If we didn't find that domain restriction, no invert allowed. All right, let's keep going. Here's one where they ask us to restrict the domain on our own. I think this is really cool because we get to see a restricted domain turn into a restricted range, and we're going to get to see something really cool happen with this function. So the first thing we're going to do is say, to restrict the domain, we know that the inside has to be bigger than or equal to, because you can take the square root of 0. So we're going to solve for that. 2x plus 3 bigger than or equal to 0. 2x is bigger than or equal to negative 3. X is bigger than or equal to negative 3 over 2. So that looks like negative 3 over 2 all the way to infinity. That is our domain of f of x, which means it's also our range of the inverse. And now that we've restricted our domain, and we said that's where we're going, we can go ahead and find our inverse. So we're going to switch x and y. We're going to solve for y. So square over the side, x squared equals 2y plus 3. Then we're going to subtract 3 and divide by 2 to get y by itself. And that is f invert of x equals x2 minus 3 over 2. All right? Where the range is negative 3 over 2 to infinity. And now that we have our domain and our range for two of the functions, I think it's valuable, even though the question doesn't ask for it, to find the range and the domain of the same functions. So because we have our domain of this function, I think it's worth finding our range for our f of x. And so the way that I'm going to do that is, instead of graphing the function, show you a different way to do it, I'm going to look at the next x value in line. And so if I plug in negative 3 over 2, I'm going to get 0, because that's what we chose it to be, right? And so our range is going to start at 0, and then I'm just going to plug in any number on the right side. And so if you look at the number line, we've got negative 3 over 2. I'm just going to pick 0 just to see, because 0 is an easy number to plug in. If you plug in 0, you get a positive 3, right? And so what that's saying is the problem is going up, or the equation is going up like that, which the square root equation, that makes a lot of sense. It's supposed to go up. So 0 to infinity is our range. And because range of f of x. And so this is a 0, right? If we have our xy graph right here, 0. And if we plug in 0, we get root of 3, which is up here. And so our function looks like that. Our range goes from 0 to infinity, going up. Going up slowly, but it's still going up forever. And now that we have our range of that, we know our domain of the inverse. The domain of the inverse is from 0 to infinity. And so I'm going to graph these two things just to show you that it all works out. We're using our two domains and our ranges. We know that the original function starts over at negative 3 over 2 comma 0, and it goes up and hits the point 0 comma root 3, and it looks like the square root function. And now if we reflect that across the line y equals x, which means we're just switching our x and our y values, we're going to start down here at the point 0 comma negative 3 over 2. That works out with our range really well. And we're going up all the way, and we're going to cross the point root 3 comma 0 and go up forever, which makes sense with our domain and our range that we're going to the right forever and up forever. All right, let's keep going. We're going to see one more problem that has a little hiccup in the middle that throws a lot of students off. So we're going to show you the trick to solve for the inverses of rational functions. It's going to look a lot like the other functions we've done. We need to check that domain restriction first. So we know from the bottom term that x can't be 2. And so our domain is going to be 2, exclude 2 to infinity. So we got every number in the world except for 2. Just a good note on the domain. We know also, because this is a rational function, that that's a vertical asymptote. So there's a vertical asymptote hanging out at 2, or x equals 2. All right, that's going to be really cool when we get done with this problem. Let's invert it. So to invert it, we go y equals x plus 3 over x minus 2. Remember, the main step of the inverse is to switch x and y. And so we're going to say x equals y plus 3 over y minus 2. Now, how do we get rid of these y's? We got two y's. We got to figure out how to combine them. The goal here is to reverse distribute or factor out our y. So let's make that happen. I'm going to multiply by y over 2 on both sides, y minus 2, y minus 2. We're going to end up with x times y minus 2 equals y plus 3. Not super helpful. We still have two y's. Let's keep going. Distribute xy minus 2x equals y plus 3. Now I see two y's hanging out. We could combine like terms to get them to be one y maybe. Let's see. So if I move this y over, I'll get xy minus y equals, and I move this 2x over, 3 plus 2x. And now I see a spot where I can reverse distribute or factor out a y to get one y out of two y's. Now we get x minus 1 equals 3 plus 2x. And to get y by itself, 3 plus 2x over x minus 1. Now this is where it's really cool. So that's our inverse. F invert of x equals 2x plus 3 over x minus 1. And you notice something really cool about this. It's not part of the problem. That's our answer, but I think it's worth pointing out. If you look at this function, you see, oh, there's a horizontal asymptote hanging out here. We do have a vertical asymptote too. That's okay. I want to look at the horizontal asymptote. The horizontal asymptote, remember, if you have the exact same exponent on your leading term, you reduce the coefficients of each leading term. So our horizontal asymptote is going to be y equals 2 over 1, or y equals 2. We'll look at our vertical asymptote from earlier. What used to be an x turned into a y because the whole point of inverses is switching x and y. I think that's a pretty cool thing to point out. You can see the same thing happen with the horizontal and the vertical of both terms. You could check it, you could graph both and see that the vertical and horizontal asymptotes switched, that all of the points on the graph switched their x and their y value, and you were left with a inverse function that looks like it's of the same form as the original function, but has every x and y switched. And so that's how we apply inverses to rational and radical functions. Thank you for watching this far. This concludes chapter 5. So I'd highly encourage you to go back and watch some videos or practice some exercises before starting your chapter 5 test. Thank you for watching this far, and I'll see you next time.